just quickly wanted to tell you what I'm working on here during my stay, so you also know what work I'm doing here. So I am visiting here. I'm here for since a month now, and I will be here for 2 more months. And here I will be working on what we call the fair stochastic figure routing with partial deliveries. And the idea here is that if you would look into figure routing with stochastic demand, you often see in literature that it's been covered in one of 2 ways. Either by using a 2-stage stochastic formulation with the recourse policy, where the recourse policy often involves a detour to the depot. So in the first stage, routes are being planned, in the second stage, they're being executed, and whenever there's insufficient capacity, the vehicle will return to the depot to get some additional capacity. And the moment on which, like when it returns to the depot in the route, different policies exist for that, but that's the general idea. The other approach is transfer strand formulation, and where you want to minimize, or you want to make sure that you can satisfy the demand of your customers in 95% of the cases, but it's often not specified what to do if you have insufficient capacity. So with the 2-stage stochastic formulation, they allow detours to the depot, but in practice, that may not always be possible due to, for example, humanitarian logistics. It may not be safe to go up and down to the depot, or just in general, due to time constraints, it may not be possible. So the problem that we will look at here, and this is in collaboration with Michel Gendreau and Walter Rey, is on the figure routing problem with stochastic demand, where we allow partial customer demand satisfaction. And we are not allowed to go back to the depot to refill our vehicle. So we have to do with the capacity that we currently have. And we're not allowed to revisit a customer. So what happens, we plan our first stage routes, we execute them, and then when we arrive at the customer, we observe the demand of the customer, and we decide how much of that demand we're gonna serve, with the idea in mind that we wanna use all of our capacity, but we also wanna make sure that all customers receive a fair share of their demand. And applications, as I said before, is humanitarian logistics, but you could also think more in general, the probability that you will sell the first product is much larger than the probability that you will sell the nth product. So you might want to distribute your capacity over different stores in such a way to maximize your revenue. But that's what I'm working on here. Another project that I'm working on that's still ongoing is dynamic fleet size and order assignment. And this is based on a canonical version. It's a canonical version of a real problem that we observed at a company, a logistics service provider. This company receives new orders each day, new requests for transportation, and it has to assign those orders to some day in their planning horizon. And the orders, they come in with a certain preferred delivery date, but the company is allowed to deviate from that date with a number of days. And it wants to do that so that it can maximize the usage of its fleet. Because unfortunately, sometimes the demand of the customers exceeds the capacity of the fleet. So the company does not have enough capacity to satisfy the demand of the customers. What happens then? Well, actually 3 things could happen. And you could either decide to not serve some customers, but that's very bad quality of service that you're delivering then. Another option could be to outsource some of the demand to different companies, but also there you cannot guarantee the quality of service that you're giving to your customers. And the final option, and that is actually the option the company implements, is to rent additional vehicles. So whenever there's a shortage on some day, the company will rent some additional vehicles temporarily to deal with that shortage. So each day, the company has to assign new incoming orders to delivery days and decide on the number of vehicles to rent for each day in a planning horizon. The rental costs of the vehicles are not fixed. It increases over time. So it's cheaper to rent a vehicle while on the fence than to rent a vehicle last minute. At the same time, the uncertainty regarding the demand of a customer, the total demand for a certain day, is decreasing as we approach the delivery day. So when deciding on the assignment of orders to days, as well as the number of vehicles to rent, one has to trade off the increasing rental costs and decreasing demand uncertainty. And we refer to the resulting problem as the dynamic fleet size and order assignment. So if we look into the literature, multiple day flexibility has been studied. I think most known problem would be the most known literature would be on dynamic vehicle routing, where vehicles might start with some predetermined routes based on demand that is known, but then during the day, new demand may come in that is either included in the current routes or postponed to the next day. And then there's some other work that even considered longer planning periods with a certain due date. For example, in the work by Arcelli, they consider a vehicle routing problem with due dates. So an order comes in and needs to be served X days from now, but it can also be served sooner. And that is somewhat related to what we're doing as well. And another option is the fleet composition, where one has to determine, okay, how many vehicles and what type do I want to have in such a way that I have best performance for my company. And in particular, if you think about multimodal transportation or single modal transportation, the barges and barges need to be booked far in advance, whereas trucks can be rented last minute to deal with any shortage you might have in your plan. So we model the problem using a sequential stochastic optimization model. We consider homogeneous vehicles with a capacity of Q, and we assume without possible generality that we have an initial fleet size of 0. We consider an infinite horizon, but a finite planning horizon with capital T, and we consider a delivery date flexibility of delta. So an order comes in with a certain preferred delivery date, and we are allowed to deviate from that at most delta days. So let's go through the model. We have a state, action, and rewards. So let's start with the state. The state consists of two main components, RT and PTT prime. RT is a set of new orders arriving at the beginning of period T, and PTT prime is the plan that we have at period T prior to the decision in period T for period T plus T prime. So it could, for example, be the plan that we have today or 3 days from now. And the plan consists of, again, two things. First of all, what orders have we assigned to that period? And second of all, what is the fleet size that I already have for that day? So an example of a state is given here at the bottom. We have incoming requests 2 and 3 in this case. And from previous states, we know that we already assigned request 1 to what is now tomorrow. And we don't have anything assigned yet or rented yet for the remaining days in the planning horizon. Then for each state, we need to take an action, multiple actions. First of all, we need to assign each new incoming order to a day within its delivery horizon. And then for each day in the planning horizon, we need to decide on the number of vehicles that we want to have. So our action at period T is a vector with a flexible, varying size from state to state because it depends on the number of orders plus the number of decisions regarding the number of days that you have in your planning horizon. Then the reward function. So what we do, orders that are incoming can be assigned earliest to tomorrow, meaning that once we have assigned the orders that are incoming today, we know exactly what we're going to serve tomorrow. That's deterministic. No uncertainty about that anymore. So the reward for a state is equal to the vehicle routing cost for tomorrow, plus the rental cost that we incur for the rental decisions that we take today for all days in the planning horizon. And then the objective is to find an algorithm or a policy that minimizes the long run expected discounted reward. So how do we compute the vehicle routing cost? Well, there are multiple possibilities here, but in general, any vehicle routing problem algorithm can be applied here. Since that's not the main focus of our work, we could use the hybrid genetic search by Thibaut Vidal or just anything that's out there. Also with the idea that if a company were to implement this, they could just use their routing tools and still make use of our framework. To keep it simple, we now just work with the cloud and write saving heuristic, because in that way we get results really fast and we can focus on the other parts. Throughout the presentation, I will refer to insertion costs, and the insertion cost of an order is simply equal to the vehicle routing cost with the order and the vehicle routing cost without the order. And the vehicle routing costs are computed by solving the corresponding routing problem using block and write twice. So one with the order and one without the order. Then we consider 4 different assignment policies: latest, myopic, greedy, and cluster, and one. So far we implemented one rent decision policy, which is non-anticipatory. So let's go over those policies. The latest policy is rather straightforward. An order is incoming, and we just assign it to its latest possible period, which is capped off by the final day in the planning horizon, because we can only make decisions for the planning horizon. Then the myopic one involves a bit more computation. So what we do here is we evaluate the insertion cost, which is the sum of the routing and the rental cost for each day in its delivery horizon. We do that for each order, and then we assign an order to the day with its lowest insertion cost. We temporarily store this decision, so we don't update the state yet, to avoid any sequence-dependent decisions. So we make this decision for all orders, and then we assign them all at the same time. Drawback of both of these methods is that the orders are assigned one at a time. So no temporal or geographical information is taken into account when making this assignment decision. Therefore, the greedy policy takes this into account by deciding for all orders at the same time. We have CR of T prime here, which is just simply the insertion cost that we computed for each request. And we want to minimize the total sum of insertion cost plus the rental cost incurred, such that each request is assigned to exactly one delivery day. And this is like a capacity constraint. So if this would be larger than the remaining vehicle capacity, we need to rent additional vehicles to increase the capacity. And the assignment decisions are binary and the rental decisions are integer. Good method, but still it has some disadvantages. One of which is the overestimation of insertion costs. Because if you have multiple orders that are close to each other, they will probably be in one route, and you don't have to do all the insertion costs will be much less. So it might be interesting to look at combinations of orders. But considering all possible combinations of orders is very expensive, because it grows exponentially with the number of orders that you have. So that's not really an option. What we do instead is we define clusters. And clusters, each cluster contains the k nearest orders to order R that have at least one overlapping period in the delivery horizon with the delivery horizon of order R. So we have a request, we look at its neighbors of new orders, excluding those that don't have any overlap because they can never be served in the same period anyway. And then we just take the k nearest orders. And then for each order in that, for each subset of orders in that cluster, we construct a bundle, and that is what we use in our formulation. So then the formulation is again the same as what we had before, but now just for bundles rather than requests. But other than that, the formulation is the same. So that order for assignment policies. What is a rental policy? Well, it's rather straightforward. It's non-anticipatory, meaning that for each day in the planning horizon, we simply derive the required fleet size from the assignment decision, and then we rent the difference with what we already have. So let's move on to the computational study. We consider 5 trajectories with a simulation horizon of 90 days. On average, we have 25 orders per preferred delivery day that then are arriving on average 7 days earlier. And we consider monthly seasonality by using a sinus function with some amplitude to simulate that. We also included a noise term to make it less predictable. The orders are unit orders, so it's just 1 unit to each customer. And the order locations are drawn from a large VRP instance. So this is, for example, how a trajectory of preferred delivery date orders could look like. So on average, we have 25, but we have large deviations, and then this is like the end of horizon effect. We consider a planning horizon of 21 days, so 3 weeks, and a flexibility of 7 days. So we can show an order 1 week earlier, or 1 week later, or any day in between, which is quite wide. But the idea here was that we really want to see whether it would be interesting to have to cluster orders and to deviate from an actual delivery date. The vehicle capacity is set to 7, which means that we can serve at most 7 customers in one route. And the rental price is some base price multiplied with a standard factory experience. So it becomes more and more expensive the longer that you wait. So these are some results. So we have the 4 policies. The assignment policies, remember, they all have the same rent policy, so that's not listed here. The idea with the latest policy is that, okay, we push all the orders to the latest moment so that the rental costs are the cheapest. And that is in fact, that's indeed what you see here. So we have the lowest rental cost compared to the other three, but much higher routing costs because no geographical information is taken into account when assigning the orders to the days. And you can also see we need a lot of vehicles. Whereas with the other three policies, we need way less vehicles. We have slightly higher rental costs, but much lower routing costs, leading to a much lower total cost. And then the performance of those three policies is close to each other, but with the cluster policy returning the best results. So how would that then look like over time? So what you see here is on the vertical or horizontal axis, we have time. On the vertical axis, we have the number of orders that are assigned to each day in the simulation horizon. With the latest policy, we keep on pushing everything to the latest moment. So on average, we have about 25 orders to serve on a day, given that that's the average number of orders arriving for a certain date. Then with the other policies, what happens is we have large peaks in our, like we have a lot of days with a lot of demand, and then we have days with no demand at all. And the reason for this is twofold. First of all, if you want to compute the insertion cost of an order to a day, it would always be cheaper to insert it, just looking at the routing cost, to insert it on a day where you already have some orders, than on a day where you need to start a new route from a depot going back and forwards to that order. And even more extreme, we observed several cases where this is even cheaper if you have to rent an additional vehicle for that day. Yeah, so that's that. And although this only happens a few times, by just making that decision once, you create additional capacity on that day, and therefore the next period you can assign more orders again. So that is why you have those peaks over the horizon. Of course, the next step is to include an anticipatory rent decision. So to anticipate future demand, make our rental decisions earlier and obtain better performance. And we plan to do that, or we are trying to do that with a stochastic look ahead. And that is also the end of my presentation, as in, let me first conclude real quick. So we study the dynamic fleet size and order assignment problem. We consider 4 different assignment policies: latest, myopic, 3D, and cluster, where we observe superior performance of the cluster policy. And our next step is to also consider anticipatory decisions. And that concludes the presentation.